Okay, so let's look at an example. In this case, I'm just giving you everything, right? The principal stresses are there, the angles are there, and we're saying a well that's oriented 20 degrees from north, so that means that delta is 20 degrees, and deviated 20 degrees from vertical. That means that phi is 20 degrees at a depth of 2 kilometers, assume a hydrostatic pore pressure gradient. So what's the pore pressure at 2 kilometers if the gradient's hydrostatic? 10, what's your rule of thumb? What's your rule of thumb? It's like, your rule of thumb is 10 MPa per kilometer. Right? I think you're confused with 0.44 psi per foot, maybe. But it's 10 MPa per kilometer. You're at 2 kilometers, so 20 MPa. Poisson ratio is 2, and you're in a balanced drilling operation, so delta P is equal to 0. So, if you go to Matlab, I have a function, compute SB. Right? So SB takes SB takes the principal stresses, the wellbore angles, and geographic angles, computes RB, okay, calls a function compute SG, which I defined already. You guys should have that, right? You used it for stress on fault resolution, right? So you should already have something like compute SG. So now I'm just calling compute SG from in here, passing through the geographic angles and the principal stress, and so then I have this. Then I can use this equation to compute SB. So, so for this problem, SB equals compute SB with the arguments. So it takes the principal stress tensor, which is 30, 25, 20. Then the second argument is the wellbore angles, which in this case are 20 and 20. The geographic angles, which are 90, 0, 0. So there's my SB, right? So again, in the principal stresses is a diagonal matrix, but when you resolve them in the wellbore, it's a full matrix, right? Now, these are still in Cartesian coordinates, okay? So, one thing we need to do is, these are not taking into consideration the pore pressure, right? So we can say SB effective is equal to SB minus the pore pressure, which was 20, right? We decided it was 20 times the identity matrix of 3. Right? So there's my effective stress. So I have another function, compute wellbore stress, which takes in my effective stress, Poisson ratio, theta. I haven't told you what theta is, but theta is the angle around the wellbore, okay? And delta P, which in this case we said it's balanced drilling, so delta P is 0. And returns all of the stresses, right? So they're just SZZ, S theta theta, S theta Z, S RR. Just to go back quickly, theta is just some angle measured from XB around the borehole. So we go back here, then we can say compute wellbore stress SB effective 0.2 theta. We'll just pick one, 0 for now, and delta P, which is 0. Right? So that just returns the first value, but we really want all of them, right? So S ZZ, S TT, S TZ, S RR. So there's all the components of the stress, but only at the 0 point, right? So then we have compute also have two functions: compute minimum and maximum tangential stress. So, for example, if we look at the minimum and maximum tangential stress, all I do there is call compute wellbore stress. So it takes the same arguments. I call compute wellbore stress, and then it uses that equation to convert it to ST max, right? And that's what's returned. So compute max tangential stress that returns ST max, right? Okay. So that's the value, but again at theta equals 0. It's more useful, I mean that's the maximum tangential stress at the point theta equals 0. But what we really want to know for wellbore failure is what's the maximum at any possible location around the wellbore, right? And for vertical wells, we know what it is, right? Where's the maximum? It turns out the maximum tangential stress is the hoop stress in a vertical well, and where's it going to occur? At the azimuth of SH min. In an arbitrarily deviated well, we don't know that up front. We have to do the computation, right? Because the stresses are arbitrarily oriented, the wellbore is arbitrarily oriented. The only way to know is to work it out. Right? And so more likely what you'd want to do is, so let's say theta equals lens space 0 to 360 in 100 increments, right? ST max we will initialize to be zeros, also 100. Okay. And then what we can do is a little for loop. So for I equal to 1 to 100. Help me out. I don't write much Matlab. Is that right? There's no. That's not there. Huh? Yeah. So it's I equals 1 to 100, right? And then ST max I is equal to compute max tangential stress SB effective 0.2 theta I 0 end. Oh, and all zeros. That's not good. Can't be right. guys. Huh? Right, theta Anybody see what I'm doing wrong? I don't really see it. Let's see what happens if I do. What? All right, I don't know what I did wrong the first time, but nevertheless, if we then plot ST max, you can see, okay, as it goes around. And now, again, I mean, I just plotted it as a function of number of points. I didn't give it an x-axis, but this is linear with respect to the degrees, right? And one thing you notice is that it's not necessarily a maximum or a minimum at 0 or 100 degrees, but that's because it's oriented in an arbitrary way. And if we were to change the angles, then it would. I mean, it's always going to oscillate like that, but it would shift where the maximum and minimums are, right? So obviously the maximum is right here, somewhere around like 40-something degrees. And so if you actually wanted to determine what the wellbore failure was, you also have to compute ST min, right? Then you have to order them, ST max, ST min, delta P. Right? Take the max and minimum of those three, and that defines your Moore circle that you can use in your Moore Coulomb failure model to determine where a wellbore failure might occur. Right? So you have to check it all the way around the wellbore. Okay.